Okay, so last speaker today is Jose Casals from MIT, and he will tell us about the differential algebra of cubic graphs. And you should switch on the mic.
Thanks to the organizers for having me. Well, Michael Colliver is not around, but I've always had a very good experience at CSG. My first paper was published there, and I like the journal a lot. Anyway,
Sure. I should have said the same thing. My first paper.
Good. Great. So the plan of the talk today is to discuss some class of Legendrian surfaces in R5, which are associated to cubic graphs. And essentially the first part of the talk is going to be pure combinatorics, and I'm going to introduce this class and discuss some kind of properties of an algebra out of a cubic graph, and then we're going to move toward geometry, and at the end, will become dreamy things that I hope they're true. So to begin with, let's start by defining what a cubic graph is. So a cubic graph, by definition, it's going to be a graph such that every vertex is trivalent. So let J be, and by assumption, we're going to assume for now it's planar. There's no actual need to assume planarity, but it'll be easy for us. So this is a planar cubic graph. There's many of them, infinitely many. Some examples that you want to keep in mind, that you're allowing double edges, so that's one possible graph. Another one is for every edge you see, you can throw in an extra edge. So this graph is obtained from here by adjoining another edge, and you can do this infinitely many times. And a classical example, which is going to be very important to us, it's this graph called the tetrahedron. And somewhat these two examples are very significant to symplectic topology. There are going to be some tori which are relevant. And what I'm going to do right now is associated to a graph, I'm going to decorate them. So how do we decorate a graph? So this is a choice that we can make, but to begin with, for every phase of the graph, we trace a path that goes from the negative part, kind of minus infinity to plus infinity, and the path can be whatever you want. So you trace a path, and the only condition is that for every phase you have, you trace one path that goes through the phase. It doesn't have to be this precise one. You could kind of go around. So for instance, some choices of path here could be these ones. So for every interior phase, I'm choosing one of these blue paths, and in here, you could, for instance, choose two parallel paths, and in here, something like that. So, and this here and here. So I call these blue paths tines, okay? So these blue paths are called tines. So for every interior phase, I put a big dot in the middle, think of the center of the phase, and I choose a tine that goes through it. The second part of the decoration for our graphs is going to be the following. For every big blue dot in the center of the phase, I trace a path, a red path, that goes to the vertex. So here's one path, here's another path, here's another path, here's another path. And then you can think there's some vertex at infinity, and I also trace path from that vertex at infinity to this one, kind of center of here. So here the same thing, you're going to throw in all these red paths in here, and then some path from infinity. So you can think it's something like that. I call the red guys threads. So this is how, given a cubic graph, you're going to put some threads, and you're going to put some tines. There's a choice of threads. I could have chosen this path, or maybe going the other way. You can, for now, choose whatever you want. And then the threads at the interior are essentially uniquely determined up to its RP. Okay. So this is completely funky, and every time I talk to someone in combinatorics, they say, "What are you doing?" Well, there's a purpose to that. And the purpose is that with that, I'm going to define something that I call a binary sequence. So here's a definition. So given a decorated cubic graph, given G and gamma, gamma is the decoration. A binary sequence along a tine. So binary sequence, this is the definition. Binary sequence along a tine. And recall that the tines are the blue guys. These are the blue paths. And this is an assignment So it's a map, if you wish, which is lower semi-continuous, and it goes like this. So B from the time, that's my blue time gamma, to 0, 1, conforming to the following rules. So the first rule goes as follows. You're going to start with your time. Let me write an example here in very big. So I'm going to zoom in one of the examples that I've written there. Please grab it here. And I'm also going to consider the set of times that I've drawn there. So here's what you do. To begin with, every time you hit an edge, that's one of these white paths, you have to change from 0 to 1. So say we start here with 1. Okay, then I assign 1 to this path, then I hit an edge and I have to change to 0. So the first rule is that if you're hitting an edge E, you're going from 0 to 1, or you have to switch from 1 to 0. So that's if you have a time like this. So whenever a time interacts with an edge, you switch from 0 to 1, or from 0 to minus 1. So that's edge E. The second rule is that whenever you hit one of these blue paths, you have to hit it arriving with a 0. So whenever you're hitting one of the centers of the face, you have to arrive with a 0, and then you will output with a 1. That's rule number 2. And now the funky one, which is why...
Times oriented?
Oh yeah, you can think of them as oriented. Yeah. I mean, you just go from bottom to top. So I start here 1, 0, and then, well, I have to switch to 1 by rule number 2. And then I must switch to 0 in here. So that will be one binary sequence along this time. And now rule number 3 has to do with interaction with the red paths. So let me for a second draw these red paths. Rule number 3 says the following thing. It says that if you're following a time, but the time intersects with the red guy in here, you can either have 1, 1, so not doing anything. A second thing you can do is, well, you're in 0 and you don't do anything. Or, and this is the funky guy, in here what you can do is, if you had a 0, you can now switch to a 1. So I'll refer to that as crossing an edge, obviously. Passing through a center, obviously, and this as I'm using the red path or I'm not using the red path. Okay? So what could happen in here? I could do 1, I couldn't use the red path here because I'm in a 1, so I have to keep being 1. Okay? Then I have to switch to 0, then I have to switch to 1 by rule number 2, then 0, and then here I have an option. I could end with a 0 or I could end with a 1. Okay, so along this time, at least I see 2 kinds of binary sequence. One that starts at 1 and ends at 1, and another that starts at 1 and ends at 0.
So couldn't it have started at 0 instead?
So if I started at 0, yeah, what I can do is use this time, use this thread in here, then switch to 0, and then you execute. So completely correct.
So that's 4 choices.
Yeah. Let's maybe say that I'm aware it's the last talk of the day, so feel free to interrupt as much as you want. I'd rather you guys to understand something than get to be clear. Okay, so this is what a binary sequence along a time looks like, and now for every time you can count how many of them there are. There might be more than one that goes from 1 to 1, because you might have lots of thread interactions that you get to use or not to use. Okay, so...
I'm still confused.
Yes.
Do you know how many is the number of times prescribed? Oh yes, by the number of regions.
Yeah,
okay.
so 1 per interior face.
I see, and the threads are similarly prescribed by entire faces plus vertices.
Yeah, I mean, the only choice of threads really is these exterior ones where I could kind of have wrapped around. So I could have chosen like these, and then these, and this other one, right? So
Why are they prescribed inside?
Autoisotopy, because it's just a path from here to every vertex.
How do I know that every region? There's no choice of triangulate. Oh no, okay.
Yeah, it's just for every center you can throw paths one to the other. Okay, so notice something. I really don't have to draw the threads here because they're never going to be used because there's no other time interacting here. So really the moment that you're drawing the threads, you only draw the threads that interact with other people. Okay, so no need to kind of draw these in these. Okay, great. So here's a graph, decoration, and that's the definition of a binary sequence. So now we're going to introduce an algebra. So consider.
One more question. Is G connected?
It doesn't have to be, but I'm going to think it is connected.
So the regions then could be multiply connected, and so the regions could be multiply connected.
If there's an island inside an inside.
Yeah. That's perfectly fine.
So there could be more than one way to draw the threads in a multiply connected.
That's correct. Yeah, that's true. Okay, so what I'm going to consider is the algebra over. Now choose a finite field. Choose any field. So for the talk, I'm going to say discuss characteristic 2 in order not to do signs. But I must say that we worked out the signs, so everything is oriented in the paper. So here we're going to take a field, and then for every edge, I'm going to introduce a variable. Okay. So now I should say something about this G number. So because it's a planar graph, Euler's formula tells you that there is a number G such that the number of vertices, it's, well, in this case, 2G plus 2. The number of faces is going to be G plus 3, and the number of edges is going to be 3G plus 3. Okay? So anyway, let's write this here. So this is going to be G plus 2, number of edges is going to be 3G plus 3, and number of faces is going to be G plus 3.
I'm confused about the formula for the number of vertices. It's 2G minus 2?
No.
So what's the genus of left side, of the leftmost? In these examples, what's the
This
yes.
is a sphere. I haven't thought about G's genus, but
Okay.
this will be a sphere.
Okay, because there's another notion of G. Okay.
You agree that the alternating sum of these guys is 2?
Yes.
You didn't tell us what the genus is.
Well, no, there is a unique number that satisfies this thing.
The answer is it's the usual genus minus 2.
Well, yeah. Okay, fine. Okay, so I have, for every edge now I introduce a variable. So for instance, for this edge I have E1, E2, E3, E4, E5, and E6. And I'm going to consider the algebra generated over this ring of Laurent polynomials, generated by the following guys, generated by the faces to begin with. So that's Fi. So these are faces. And the second thing that we're going to use as generators, it's 3 guys, X, Y, and Z, which I'm going to explain in a second.
Is that just interior faces?
Sorry?
Is it just interior
Yeah, that's
faces?
correct, interior faces. Okay, so now the Fi's are going to have degree 1, and X, Y, and Z are going to have degree 2. Okay, and the edges, well, you can think it's a ring over here, or you can just think that the edges are generators in degree 0. These are here. Degree 0, guys. Okay, so this is a graded algebra just by formal multiplication, and now we're going to introduce a differential.
Non-commutative, right?
You can take it to be non-commutative. Let's assume that it's commutative today.
No, the E's are commutative, but also the Fi's and the X's are.
There is no reason to do it commutative.
Okay, but let's
life
assume-
is
okay,
beautiful.
okay.
Yeah. So we now introduce a differential. And a differential, it's something that's going to depend a priori on the choice of decoration, and it maps our algebra, and it decreases the degree by 1 into itself.
So is it a free algebra? No.
It is a free algebra generated by those guys, just formal product. So let me define the differential. So I have to define, it suffices by extending by Leibniz rule to define the differential on the generators. So I'll tell you first what the differential for the faces are, and then tell you what the differential of the degree 2 guys are. And you're allowed to be very confused about the x, y, z until maybe in 10 minutes it'll become clearer, maybe 20. So here's the differential. differential LG and gamma G is defined as follows. So first of all, the differential of a face Fi is just going to be a combination of the vertices of the face. So what I do is I just take the sum for all the vertices in our face of the weight of the vertex. And what is the weight of the vertex? Well, in here I have the vertex V, and in here I have the face Fi. Then, well, there's going to be some edges, Ei, Ej, and Ek. The weight of the vertex, by definition, so this guy in here, that's going to be, by definition, you multiply the edges which are inside the face, Ei and Ek, and you take Ej inverse. Okay? I'm going to do an example about that graph in a second. And now the differential of x, y, and z is going to be way more exciting. So what I'm going to do for x is to count how many sequences are there from 1 to 1. So I'm going to take b to be a binary sequence from 1 to 1. So let this curly b be the number of binary sequence from 1 to 1. So for each thread in each phase. So for
Each time.
yeah, for each time, maybe let's call the times gamma f, and for each binary sequence on the time, I'm going to assign some value to this time times b, and then this is times, well, the phase itself. But of course, this is a sum over sums. So for each given phase, you can have different b's. So really, I should be writing the sum over. So I start with the phase. Maybe let's write this properly. So for each phase, what I do is I pick a time associated to the phase and some binary sequence. And then each binary sequence is going to have some coefficient in here. So
But
this
it's
is
not dependent on which phase. Oh, sorry, it's my effect.
So this is a monomial in here. Okay. So what I'm going to do, I'll boil it down in a second. Given one of these binary sequence, I'll associate to it a monomial in the EIs. It's going to be some product of the EIs, which I'm going to explain now. And so now, given x, what you do is you first look at this time and say, how many sequences do I have from here to here? And for each one of them, you assign a monomial in the E's variables. And you do that for every one, but you're only counting 1 to 1. Okay? So, example in a second, but dy will count, I'm only writing it, so that will count 1 to zeros, and this is going to count 0 to zeros. And yes, there is a reason I'm not counting 0 to 1s. It's a good reason. So let's compute in a second what can we get for that guy. So for that, I have to tell you what kind of contribution do you have every time you have a binary sequence. So in the example there, well, for instance, you can take what's del of f1 if f1 is this phase in here. Well, del of f1 is going to be e2, e1, e4 inverse coming from this vertex. So that's e1, e2, e4 inverse. And then from this vertex, we're going to get a contribution of e1 and e2 and e3 inverse. Okay? You can work out, I think, f2 and f3 on your own. Okay, so we have some numbers. So now, what about del of x? So, okay. So here are the rules for del of x. Every time you go from 1 to 0 along an edge E, the contribution that you're getting is E inverse. And every time you go from 0 to 1 along an edge, like this, using upwards all the time, yes, you're going to get an E. There's no contribution when I hit the center of the face, and the only third rule you have to remember, so this is related to the first rule I had, is that whenever you use a thread, then you're going to put exactly the weight of the vertex associated to that thread. So whenever you have this path, red path, and you're going up in here. This red path is going to end up in some vertex v. So if you're using it, which you can only use by changing from 0 to 1, then the contribution of this guy is exactly the weight of v.
So relative to which region around v?
Relative to this is coming from a face, right? All the red guys go from the center of the face.
Yes.
Okay, so relative to here. So it's this guy, inverse that guy. Okay, so let's see this guy how it looks like. So here, if I'm starting with a 1, I cannot use this red path, I cannot use this, I have to switch to a 0. I'm okay, I can switch to 1, then switch to a 0, and then I get 2 choices. Okay, then I can either switch here to 1, or instead stay 0 and switch here to 1. We agree with that? So this F1 guy, it's going to give us 2 binary sequence from 1 to 1. What is the contribution? Well, first of all, we're going 1 to 0. So each one of them is going to have an E1 inverse. Then there is nothing. And then I go again from 1 to 0. So again, E1 inverse. And then you get to choose either this vertex or this vertex in here. If I use this vertex in here, it means I'm using this red path. And so the contribution that I get is E2 inverse, E1, E3. Or I could have chosen the other guy, in which case I'll get E5 inverse, E3, 6. Is that clear? So this will be the coefficient in front of F1. And now you do the same for F2. And as we saw, there's only one binary sequence in F2, which goes from 1 to 1, which is 1. I cannot use that. 0. In here I'll get a contribution of E4 minus. 1 to 0, E3 inverse, and then use this red path, which will give a contribution of E5 inverse, E3, 6. Does it make sense? Okay, so plus, okay, where are we? So, ask me later otherwise. But the point is highly computational, both the degree 1 and the degree 2. So now comes the main theorem, which is, this makes at least some sense algebraically. Okay. First theorem is del squared is 0. And also, this is independent of the choice of the garden, of the decoration. So, that's the theorem, that's part A. So del gamma is 0 for any decoration gamma in a given graph. And the dg-algebra isomorphism type does not depend on gamma. So this thing, so that's A associated to graph, and then the differential depends on gamma a priori, is independent of gamma. For the experts, this is slightly better than you would expect in fluid theory, in that this is not a tame isomorphism, it's an isomorphism on the nose. So, a bit better. And now part B, which makes this a bit more exciting, is that the augmentation variety of this algebra, that's the set of morphisms from this guy to a certain field with a 0 differential, is actually something interesting. So in this case, let's set a finite field FQ with Q elements. So this augmentation variety. Anyone wants to have a guess? So the number, let's put it this way. This augmentation variety, which I might call x sub q, well, this has a number of fq rational points. So that's the number of fq rational points of this guy.
So sorry, what is the augmentation here?
Yes. Okay. So let's define it. So this is okay. Let's put it like that. So this is the number of morphisms phi from my algebra to a finite field Q. Okay? And the fact that this is the dg isomorphism, it tells you that if you first do del homomorphism, tells you that if you do del first and then phi, that should be the same thing as doing phi and then del here, which is 0. So this is just tantamount to the equation that first doing del and then doing phi, this should be 0. In layman terms, you have del, for instance, in here, this is del, and then you have to send this to 0. So it's some assignment of these. You're going to send the E1 to one element, E2 to some other element. You get to choose those guys, and the only constraint is that those equations should be satisfied for the faces. And x, y, and z go to 0 because it's a graded. It's a differential graded homomorphism. So this is the FQ mutation variety, so has as many points. So it has exactly as many points as Q plus 1 colorings.
Okay, now I'm confused again. So is it a graded homomorphism?
Yeah, it's a graded.
So it means the fi's and the x's must map to 0, right?
The x, y, and z go to 0.
And what about the f's?
Oh, the f also go to 0.
Yes.
Yeah, but
So it's only about e's, right? You choose the element of a field for each e, and the relations are that
yes,
the things corresponding to the d of fi must be
that's correct. So to be completely transparent, I could have done all that without mentioning x, y, and z. Like this differential is only imposed from the faces. But what this is saying is that this binary sequence algebra that I've cooked up has some interesting information combinatorially. It's saying already the degree 1 part, that recovers colorings of the graph.
So and now I'm confused because A was defined over some field itself, right?
Oh,
What's
yes.
the relation between the field of definition and Q? Do I need the characteristics to match, or what's the?
You,
Because it should be linear over the ground field, or not? Or
yes.
Of course, you did characteristic too, but presumably there would be a version.
Let's put it this way. Let's take fields of characteristic 2, but of number of elements 2 to the k,
Okay.
and I can use this for finitely many k's, and that determines the chromatic polynomial.
Okay.
Maybe it's a bit cheating, but
Okay. Anyway.
yeah, I mean, part of this should be read as this algebra recovers the chromatic polynomial of the graph. You could evaluate it at a bunch of points, it's a polynomial, so at the end that's enough. Okay, so hopefully part B justifies, or part A explains that this is somewhat canonical, and part B justifies that this is combinatorially interesting to some extent. Okay, good. So, yeah, so I'm going to move on to the geometry instead of start proving this theorem. So that's exactly what's proven in the paper that's online right now.
So what's the coloring? It's a coloring of what?
It's
What do you
doesn't
call it?
matter, so of the faces.
Even for the augmentation assigns elements of a field to the edges.
Yes. Yeah, that's correct. That's coloring of the dual graph. Tell me, Elsa.
When you say dependent declarations gamma,
Yeah.
I didn't really simply times the some mistakes in that. You're having them always oriented from bottom to top. Is that just a convention? Like, could I switch the orientation of them?
Yeah, it's completely conventional. But instead of this time, I could have kind of, done the time like this, like went around
Yeah,
and then.
and the times themselves without intersect.
Yes, but let's not assume that. So certainly for independence, one of the things you have to prove is that if you let the time cross a vertex, that's independent. So that's a count of binary sequence on one side of the vertex versus a count of binary sequence on the other side. And what you do is you prove that they are the same on both sides. So there's one thing is this one, the other one is if I have two times which are parallel, associated to a face here and here, whether I can change the order of the times. So there's a bunch of combinatorics you can do. Del squared equals 0, well, I'd love to talk about it. I'll just say that what you do is you start with a guy here, and then for every thread that you have out of it, you define a continuation of this time. And then you foliate this, and you go to another time, which has a negative sign. Well, just to say for those which are familiar with small lie spaces in Floer theory, it is a Floer theoretical proof. though it's only using combinatorics. I want to get to the geometry, so.
Is there an easy way to know how to perform an augmentation to a coloring?
Sorry?
Is there an easy rule for how to perform an augmentation to a coloring?
No.
No. Okay.
And I mean, well, the answer is it's going to be as easy as going from an augmentation to a sheaf.
Okay. So
So,
as well wait a
Yeah,
little bit.
we can do it, but
That's enough.
it takes some time. But yeah, I'll explain that in a second. Okay, so let's do some geometry now. So I want to justify all that. And this goes back a year ago, exactly in the same room where Eric Zaslow was giving a talk, and he said something that looked completely outrageous to me. And well, we started to discuss, and the conclusion is that, well, these things actually make sense in certain contexts. And what he was saying is that you can construct a Legendrian out of these graphs, and then what he would do is compute sheaves on it. And I want you to understand what was the saddle-morphic geometry in there. So first now I'm going to tell you how to look up a Legendrian from one of these cubic graphs, and then I'm going to explain how to do saddle-morphic curves in them. Okay, so step one, compute up a Legendrian. So let's start with the talk. Legendrians. So these are Legendrian surfaces from graphs. So one thing I could do is just draw a front and tell you, well, that's how Legendrian looks. Let's do something slightly more elementary, which is let's look at the first jet space of C. So these are J1 of F, where F is a map from C to C. So I'm keeping track of the values of the map F and the first derivative. So J1 of C has an holomorphic complex contact form. So this is an holomorphic contact structure. And what I can do is, every time I have an holomorphic contact structure, I can just take the same u's and v's, take the real part or the imaginary part of W, and I'll get a real contact structure in R5. So this is the same thing as R6, because it's T star C times C. And then, if I just take the same v's and the same u's, the real and the imaginary parts.
Maybe you should tell us again. So U is the variable on which F depends. So it's like W equals F of U, and V is.
Yeah, so that's correct. So W is F of U, so this is U, this is W, and V is going to be F prime. And the fact that you're Legendrian tells you that you're in the kernel of that, which tells you that the contact structure is generated by the germs of J1s of this thing. And what you can do now is that, well, W might be something like Z plus I times T. U might be X1 plus X2I. And then V might be Y1 plus IY2. And out of here, by taking the real part of W, what I get is a contact form, which is dz minus, so that's taking real parts of everything. That's going to be the real part of V times the real part of U, so that's going to be Y1 dx1 minus, well, there's a sign somewhere. Okay, this thing, and then Y2 dx. Okay, so if we take the real part of this, we get here. So we've gone from being to C3 to being to R5. Okay. So now I'm going to draw the simplest possible holomorphic Legendrian, which I can think of, which is not smooth. So the holomorphic cusp is the equation given by UVW. It's going to be T squared T cubed. So if I ask somebody to write this in the real plane, that's pretty easy. The projection that you see downstairs in the real plane would be something like this. That would be in the UV plane. And then in the UZ plane and the UW plane, you would see this. Right? So this is kind of baby contact topology. But now I'm taking the holomorphic guy. So now the claim is what happens to the holomorphic front. So the front of this basic singularity in coordinates RU, B is the following. So I'm going to take the U plane, so that's the x1 times ix2 plane, and then I'm going to draw the real part of W. And that's how it looks like. It looks like this. It has a very singular point in the middle, then it has some edges, which are going to be singularities, and then what you see in here, it's some doubling of the plane. Okay, so that's how the real part of complex cusp looks like. Okay, so in the real plane you see this cusp, that's a singular point. The singularity that you see in the complex plane is this one. And look that there are no codimension 1 singularities. There shouldn't be because it's a complex singularity, so there are no real codimension 1 singularities. It's just real codimension 2, which is this guy. Okay, so what this is saying is that every time I draw these in this 3-dimensional space, I get a Legendrian lift in R5. So this front lifts to a smooth Legendrian. This front lifts.
So I'm confused. Along the edges, you just have that the two sheaves cross each other. It's like half plus minus something that.
Yes. Okay. It's these edges. Let's maybe put it like that. If I did slicing here, what I would see would be the following picture. I would just see this thing, and then I have one coming from
No, it's
here.
not for the generic thing.
And then here it's not generic. It's actually not even Legendrian stable. You can perturb this to Legendrian stable thing, which I will do in a second. Okay, but it's an isomorphic singularity, and then it's isomorphically stable, not really stable. And so what you can do is, given any graph, you can now apply this construction to every trivalent vertex. Okay, so what do we get? So, well, let's start with a very basic graph. So maybe let's draw this graph in here. What's the front of this graph? You have to describe a surface in J1 of S2. Okay, so this is the plane. So this gives a Legendrian surface. So this is G. This gives lambda G in J1 of S2, described by its front. And how do you do it? Well, you take each face and you take two sheets over each face. You do flop. Okay, you kind of do write it like this. You kind of think of it as doubled. Here doubled as well. And here like this. And you close up from the other side. Okay, so every time you see one of these things, it's going to be double like this. And in here, you're also going to go out like this. And this singularity that you see in this side is exactly the singularity here. Okay? So we've agreed that this leads to a Legendrian disk, a smooth Legendrian disk, because it's just a standard cusp singularity in the front. And so what this allows me to do is, given any planar graph, it allows me to draw a closed, immersed surface, particularly singular in here, in R3, but actually because it closes up is in J1 of S2. Okay? So this is a Legendrian surface in J1 of S2. Good. So in this case, this is a sphere. So this is going to be a sphere. And now let's do this example in here. This example in here, it's going to give us a Legendrian torus. So that gives a torus in J1 of S2. And the G I've described at the beginning of the talk is precisely the genus of this Legendrian G. Okay? So again, the way you do these things is by this double bubble construction and move away. Okay? Is that clear? Okay. So now, what do? Well, now you do SFT, or at least Legendrian convex homology, which is you study the possible set-holomorphic curves whose boundary lie in this Legendrian. Now, there's something that I have to say, which is slightly technical, which is you shouldn't really count in J1 of S2. The right space you should be counting on is R5. So in fact, and sorry, but I have to say that because otherwise it's not true. We include J1 of S2 in R5, and the Legendrian.
Wait, how does it embed in R5?
I'll do that in a second. Becomes, let's say, this guy, Twiddle. So here's a baby example with a knot. If I have J1 of S1 in here, I can think of it as an infinite wall, and then I can draw something like this. Right? That would be a knot in J1 of S1. Now, the way you include this thing in R3 is by taking the closure of this guy. So the closure goes as follows. You're going to take the same thing in here, and then do this. Okay. So is this picture for knots clear? I have a Legendrian front, and then whenever I see the ends, I pull this guy up, and I pull this guy up. And I think of this as being the front in J1 of R, if you wish, R3. Is this transition clear?
Sorry, so this zigzag thing just corresponds to taking S1 and embedding it as a round circle, and so that this neighborhood of S1 we can think of as a solid torus that will sit inside the R.
Exactly. It's that guy.
Okay, so the edge cusps just come from bending of solid torus.
If you
Okay.
do like smooth braid theory, you can do that. But then in here you get the cusp.
Okay, just from thinking of a knot that this is going along.
Yeah.
Okay.
It's literally doing that. I could have chosen another knot and
Well, that's
put it,
fine. Yeah.
and then I'll do that. Okay. So now that we have these guys understood in the knot case, you can understand how this works in here.
Well, similarly, so I embed this in neighborhood of the standard Legendrian and not S2 also.
Exactly. You put these in the standard S2 inside of R5, and then when you have to choose is a phase in here. You have to choose a phase, and then open it like this. So given a phase now in the two-dimensional case, a phase in here will have typically over it two guys. We'll have a sheet here and another sheet here. And what you're going to do is you're going to close up these sheets like this. The closure of the sheets now is going to be like that. Like this, and now rotation of the bearing.
But the outcome should not depend on which one I
And
choose.
it doesn't depend.
Okay, but it's like sliding the stuff now.
That's exactly it. Yeah. For maybe people who are more 3D topologies, I like this set of Legendrians a lot because it generalizes the braids in dimension 1. So in here you could have 2 braids or 3 strands. So in here you could have kind of a braid here, another braid here, and then concatenate them. And that's exactly what Peter was suggesting. Like put a graph here, put another graph there. So whatever you can do with braids, you now can do with Legendrian surfaces. This is kind of a 2D analog of a braid.
But when you talk about braids, right, there were no crossings initially, but just by choosing Legendrian and left, all the crossings go the same way.
Again, I mean, these crossings are always this one.
Yeah, exactly, they're always this way.
Yeah, that's
and,
correct.
and so similarly, there's a standard notion of what to do along the edges.
Yeah, there's a unique lift of that thing.
Yeah.
And what I'm saying is that you might have a complicated braid, and now think another complicated braid, and you can compose them.
But the positive threads, not that.
Well, yeah, I agree, but if you put like several strands. Yeah, anyway. Good, so now we have these Legendrian surfaces in R5, and we can start doing isomorphic curves. And that's the following theorem, which is what I've constructed before actually recovers all the isomorphic theory contained in those Legendrians. So, theorem. So the binary sequence algebra, so the algebra, the dg-algebra of binary sequences recovers the Legendrian contact homology, or even the Legendrian algebra of those guys, closed upstairs. So that's the algebra from SFT. Okay. So maybe a remark is in order. So what kind of dga? Well, it's the full dga. It has all the homology coefficients you wanted. So in fact, what you do is choosing a spanning tree for the graph. So choosing the spanning tree T and setting all the other edges EIs to 1 for the EIs not in this tree is exactly our Legendrian dga. I'm slightly lying because there's a vertex that you have to take out, but that's the message. It's exactly the Chicano-Ashford dga.
Now I'm completely lost.
Okay.
I thought I understood vaguely until Doraemon, and now I understand.
Sorry. Okay. So first of all, we had a dga at the beginning of the talk.
Yes, and now we have the GA.
And now we have another
That is
GA.
how they are related. Because I thought I understood generators for the faces coming from the chords that you live in the middle of the difference.
That's perfect. Yeah.
I don't understand anything else anymore.
These were the red chords.
Okay.
Okay, good. Which corresponded in the graph to these bubbles. Red chord here, red chord here, red chord here, red chord here, red chord here.
So these are the Fs.
These are the F's. Perfect. I's.
And for the unbounded face, is it the same or is there something funny because of
Well,
the folding?
first of all, because of the folding, we've killed the unbounded face. So that's why I'm not taking into account the exterior face.
Oh, but it didn't have a generator, that's right.
It didn't have a generator. And now the key point is y, x, y, and z. Well, look at this picture. In here, I'm adding,
But what about EIs first? There were generators for the EIs.
yes, degree 0. Okay, the EIs are the homology classes. These are the homology coefficients.
Ah, no.
Yes. Okay. So that's exactly the remark, and that's why. Yeah. Okay. So if I take all the EIs and cook up the algebra, that's going to be some algebra. That's more information than the DGA itself. The DGA is going to be an algebra.
So which DG?
That's correct.
They're all DGs.
They're all DGs. So if we want this algebra, the Legendrian, the Chicano algebra, associated here.
What if you put recovers as opposed to is equal to? I see, so you're saying this recovers means set sum of the EIs equal to 1.
Yeah, that's exactly it. And if you want to be really fancy, you take a GAD quotient by some action, but maybe we don't want to be fancy. Okay, so if we want this guy with coefficients in the homology of the Legendrian, or maybe I should say the field. So this guy is going to be generated by some EI up to e to j. It's going to have some gamma. Okay. So there's way less here than the ones I started with. So what you do is you choose a basis of the homology given the edges. And my claim here was that a way of doing that is choose a spanning tree for the graph. If you choose a spanning tree for the graph, those edges generate.
But confused, isn't the spanning tree for the most basic graph, it still has one edge?
Yeah, that's why I said small parentheses. What you do is a spanning tree for the graph minus vertex. So you take out a vertex, and then you choose a spanning tree for the rest. So once a spanning tree here, let's take out this vertex, this is a spanning tree. So that might be the generators of the torus, mu and lambda. In here, there's no spanning tree once I remove that guy.
And when you say this, I don't know how this give me loops on the little map.
Yes, okay, I can discuss that.
Maybe that's not important. If it's not important,
No, I mean, I think it's relevant. So the remark, so note that each edge of the graph EI gives a curve, closed curve in the lift associated to that guy. How? Well, what is this? This is a disk, double branch cover over itself at one point, still a disk. This is a disk with 2 branch points, so it's an annulus. That's the zero section of the annulus. You start going, if you wish, up in here, you go down, you go up again, you go down, and you go up again. Very good. So this thing is the same like this. This guy here. That way. So each of the edge gives the guy in H1, and what I'm just saying is set one of the EIs to 1, such that the rest are still a basis, and then you recover the Legendrian SFT dga with homology coefficients. Okay. And now I'm going to give you a 30 seconds proof, which is I'm going to tell you exactly why you have to use this red path for trees. So first in here, so let's do a big example. Let's imagine I had a very long braid like this. And then we chose this closure. So what is x, y, and z? Well, as Denis was saying, these are the faces. And now this is going to be x, this is going to be z, and y is going to be this one. I claim that there is a perturbation such that at most there are chords here, here, and here. If you like the Lagrangian projection, this is going to be a crossing, this will be a crossing, this will be a crossing. So these are the inversion points of the Lagrangian projection, which correspond to red chords. Now, what's all the deal with the 1s and the 0s? Let's look at x. How do I get an homomorphic disk? Well, this guy upstairs is going to end up in here. Doesn't matter what the guy downstairs does. So now, how can I close this up? Well, I better do whatever I do here, maybe use this red chord. So maybe I can start here, use this red chord, and then go down. Maybe also use this red chord, also use this red chord, and then end up in here. So the 1s and 0s, what they do is they keep tracking which of the two levels are you.
I see upper or lower. And so I see when you cross an edge, you must cross.
You must cross, yes. So if you're in x, you want to start in 1, because that's where you start, and you want to end up in 1, because you want to close it up. So x counts 1 to 1. Now what about z? Well, z is going to end up downstairs. So I start at 0, it better end up at 0. And now what about y? Well, it starts 1, but this upper guy goes to 0, so it better end up at 0. So that explains the switching in the edges. It explains why I'm counting what I'm counting.
You didn't quite tell us why it has to happen over a time.
Oh, yes, that's technical. I mean,
yeah, okay.
There is a metric such that those are the rigid flow trees. That's the answer. Yeah. So let me at least explain why the red path does some funky thing. And it doesn't matter if you don't understand. It's going to be a picture. Store it, and someday maybe it will make sense. So that's the picture. That's what I'm claiming is that's the only homomorphic curves that you have to take into account whenever you see these special type of Legendrians. So here's proof, or sketch of the proof. So there's one special homomorphic curve, which I call the sneaky tree, and it's as follows. This justifies the red path. So let's look at a vertex. So first of all, at a vertex, I have this kind of bubble. There is, at least myself, I don't know any reasonable way of understanding that guy in this non-perturbed form. So the first thing you do is you perturb this to a Legendrian generic singularity. What is a possible perturbation? Well, it's as follows. So it looks like that. You recall that these look like this, very singular point. So what you do is you extend this a bit more, you extend this a bit more, and you extend this a bit more. So it's going to look like this, and like this. And now what do? Well, recall the boundary conditions. This is still this thing. This is still this double bubble, and this is still this double bubble in here. And now, what kind of singularities should I put? Well, in here, I'm going to have a swallowtail. Swallowtail is going to be born here, here, and here. And then the cusp edges behave like this. Okay, so this is swallowtail singularity whose cusp ends up in there. Does this picture make sense?
I'm confused about the bottom red arc passing above the triple point. Is that meaningful, or what does it mean?
The bottom, this one? No.
No, but why does your red triangle not answer for the triple point? Is it meaningful that this bottom edge of your red triangle passes above this? What does this mean?
So this is all up. It's all up. It's a.
Up inside what?
So
it's a bit trying off pavement.
yeah. So maybe let me draw it from another perspective. So this is what you see. You have one swallowtail point living in here. So in here you don't see anything, and in here you start seeing this swallowtail being born. That's what you see as you slice that way. And then this cusp of the swallowtail is allowed to kind of continue its own way. And this is going to continue another way.
Got it.
And then it's going to die.
And this always happens on the one sheet.
That's or either above or below.
But the perspective.
This is what's called in Arnold's ICM address in singularities of ray systems, d4 minus singularity. That's if you want to go from this to the top to this to the bottom, you pass exactly through that holomorphic singularity. Okay, so that's our perturbation of that triple point, and here's a tree. So I there claimed when I was doing the combinatorial that a blue path, which was exactly this Morse flow tree, could go to a vertex by using a red one. So what is that guy? So what this guy is you're going to start with the path upstairs, which it's in here. And then, sorry about that. And then what I claim is that this guy can split off something below, and that guy is going to enter this region. So the claim is, in this local model, I can choose a metric such that if I start here, there's only one way in a rigid tree that you can end. And I'm going to draw that way. Okay? So here's the way. You start with the point upstairs. The point upstairs starts moving inside, so does the point downstairs. And now the point upstairs uses this guy and starts going up. Okay? We good with that? And here there were two sheets, and now when I cross this edge, this guy can go up. And so now my tree looks like this.
Like go up means jump forward.
No. It just, I mean, it's literally like this. I had my tree that, well, let me draw it like this. I had the core here, and then the next move that I see, it's this guy. So what I'm just saying is the tree does this.
Okay.
Like kind of coming from here. Okay, next thing that happens is this tree uses this cusp. So what I'm saying is the tree now starts doing that, hits this vertex, and then comes back. So now this guy is in the upper sheet, and the lower guy is still in the lower sheet. And now the lower guy can use this edge. So now I'm going to find myself in here. So the only thing I'm saying now is that the picture is exactly this one with a crossing in here. So I started with this tree. I started to move up. Now, obviously in a 1D picture that's not legal, but what it does now is it moves the other way in the upper side, and on the other side it moves like that. This is the same tree. It's 2D. Okay? So now the point is that I have now reached something which is in the upper sheet out of the two ones here. This is in the upper one, so this lower thing can now go inside and use this edge to go up. So it itself now can use, I mean, you have to have 2D kind of creativity that now this goes up, but these two guys are the same. So the lower guy now does the same thing that the upper guy had done before. And now you can use this edge in here. So the total tree, it's like this. The upper part starts to go up, hits an edge. The upper part does this, both they get in, and then they at the end. And the claim is that this is the unique rigid Morse flow tree that you get. And you have some index formula, you count the number of edge intersections and cusp ends, and that's index 0. And I claim there's only this one. Okay? And that's exactly the guy that contributes, because every time I have two guys, I can just split off a part from outside, and this part downstairs is going to die. So I was at 0, but then I split off the guy downstairs, and I keep 1 being 1, and that guy is going to die in the vertex. And that's interaction of the blue and the red. So that explains that if I have this blue pad and I'm using the red, in here I'm going to have a tree which was at 0, so it looked like this. And then when I hit this, the tree is going to be divided in two. One part is going to go one way, and I don't know how to draw this properly. Kind of, this part is going to go its own way. They split out. Okay? So this now continues to be 1, and this guy goes down to the vertex and dies. And it does this trick here. Okay? Yeah, I mean, I'm not. I know this is a bit unconventional math, but yeah. Is this switch understandable? That I was in the bottom at 0, and now the tree breaks up in 2.
Yes, yes.
So it has something that goes from here to here, and another thing that now it's 1 to whatever it was. It's clearly far away. Okay? And now the 1 continues, and the 0 does the sneaky move and dies.
And the boundary went over an element of H1 that corresponds to your vertex weight. So
Exactly that. The homology class of this thing is EK, EI, EJ inverse, because it's just the intersection with these cycles. Okay, so that computes the homology. Okay, so that was first third of the talk. So let me just conclude a bit and say, well, you can arrange the metric such that the only trees are along the tines, the rigid ones, and the only thing that happens in the vertex is this thing. So you've computed the dg, and it conforms to the algebra in combinatorics described at the graphs. So great, so maybe I should say something now, which is this theorem proves one case of the famous slogan, one famous slogan nowadays. So corollary for Legendrian surfaces coming from graphs, and now the slogan that you want to remember is augmentations or sheaves. Why? Well, augmentations are colorings. That's some of the things we proved. Yeah, coloring. Yeah, thanks. And, well, you compute sheaves, and sheaves are also colorings. So you're done. Okay, so I'm going to finish in 20 seconds. What's really interesting starting from here? Well, all of this is algebra. And, you might believe in isomorphic curves being everything and such, but I believe that geometry is better. So what goes next after this is a calculus of how the geometry underlies graphs. So for instance, imagine I had a graph with an edge in here, and now I change it by a graph with an edge added in here. So question, is there a relation between this Legendrian and this Legendrian? Imagine, for instance, another move that you can do is if you have this graph, can you now change it to something that, for instance, has only these boundary conditions? Does there exist a Legendrian geometry behind that? Claim, another theorem, this is a one-handle attachment, this is a two-handle attachment, much better than that. This thing, if you have two graphs like this, and you substitute them by this is a Legendrian connect sum, so now allows you to do lots of stuff. And maybe the big finale, for those who have studied with cluster algebras, this thing exchanged for this thing, well, I guess it's a mutation. And the good thing is that because we understand the geometry of this move and this move, I can go from here to here in another way. I can think of this in two steps. I can first do this and attach an edge. Is this a one-handle attachment? No, because it's not that guy. But this movement, attaching an edge in something adjacent, that's the same thing as connecting some with this guy. Right? Because if I remove this vertex, then I'm going to insert a triangle whenever I had a vertex. Sorry. Yes. Imagine I had a graph like that, and then I have this graph in here, right? And now I change, this is one vertex, right? And now I erase these, and I connect. So what I've done is substituted the vertex by a triangle. So here what I'm doing is I'm taking this vertex and substituting it by a triangle. And now you can erase this edge. Erasing an edge it's this hand moving here. So this does this, which tells you understanding a mutation is the same thing as understanding connected sum with this guy and a 2 handle.
No, if you erase that H, you don't get what you say.
Yeah. I mean, this is going to be this.
Oh, that's what you mean by erase.
Yeah. Sorry, that moved too. So mutation, which is a pretty decent thing in cluster algebras, is now geometrically understood as connect sum with this guy and attached to handle. Anyone has a guess what that guy is? That's the Clifford torus. So really what's happening is that the Clifford torus has no exact Lagrangian fillings, it has non-exact fillings, and the difference between Clifford and Chekhanov is precisely this move. So whatever you do is you take a one handle and you think of it as Chekhanov torus and you substitute it by the Clifford torus. And now then it has a vast computation of Maslov this. So what this does is it recovers this thing geometrically, explaining why these two J's allow you to do that. So I'm going to finish. Thanks a lot for the extended time though.
Okay. Any questions? Are we all overwhelmed?
Sorry.
Okay, then maybe we should thank Roger again and we can digest and have questions about dinner. So dinner is at 6:30 in the math department, that's in the science center. If you don't know where it is, Google Maps does or follow people. Oh, do we have any access issues to get into the science center at 6:30 or is it open?
I think you might by 6:30, yes.
So what's
No, don't worry about getting into the science center, it's just, and you can also go up the elevators to the 4th floor, which is the level where the common room is, but there'll be a corridor on the 4th floor and the door might be locked, but just wait 30 seconds and someone will come by. And
I see, so the science center itself is open, it's just the 4th floor.
it's just the
entrance,
math
but
department's
maybe- okay.
corridors, which
Yeah, I think we can indicate that one, that's
Yeah.
Okay, and tomorrow morning we resume at 9 a.m. I think you skip that picture with the three square rotates and things. Understandable to the three. Yeah, but I think it part. Like, I mean, because the whole thing of performing into three square rotates and then developing it. I mean, it's not feasible for people who are experts in the kind of photography to anything or somebody like surgeries. I think that part is. I think we're happy to trust to have some thing that happens there.
Now it's great.
I guess
I just want to convey the
Sorry? Yeah.
Thanks, no.
I think what you can do is that people like
Yeah,
you
by the way.
can see the can see that there's a picture of the basis. And I think I'm beginning to see some of it, but you know, it's just
You were here for a while, right? You recommended. Oh, yeah.
So what
A while ago, but for a while, yeah.
Yeah,
sheaves are 4 years.
Every
4
phase
years in total.
now bubbles up like
4
this.
years.
So now you have the zero sheet inside, the
2000.
vector space inside of space, and outside C2.
Oh, that's over here, okay.
Okay, so it's 0 C squared over M.
And now the two faces are adjacent, corresponding
That's
to
2006, I was
these
at 12 when you were
push
there.
out.
So you have transverse flags at each crossing.
Oh, yeah.
No, actually, Edward is surrounded by the
So this is going to
I think you were around.
You're
No,
maybe
94. 94. That's right. Now you arrived around 9.
Yeah, but it's your
I remember talking to you last when you started, but I wasn't asking to do it.
Sure, of course.
So now
Very
what
much
I'm
in
doing
front.
is-
Oh, I see, what you're saying is this corresponds to